Hello everyone, my name is Riccardo and I work in the software team at LINX, and I'm here to talk about the network configuration automation platform that we have built at LINX. We're currently using this platform to deploy changes to our main peer in LAN, London 1, composed for the majority by PTX and MX hardware. Nevertheless, our platform has been designed to support multi-vendor hardware, as I'll explain more in detail during this presentation. So we model our platform trying to fit into the organization predefined processes to run the network. And we're concentrating in automating the most repetitive and routinely part of the network engineering job when deploying a change. So this part is the actual manual changes to the single switches configuration. So from the network engineer point of view, the user journey is pretty straightforward. So as usual, anytime that they want to deploy a change, they will need to update the inventory data, both hardware inventory or service inventory. And then at that point, instead of actually going to the single switches and applying the changes, they will use our platform through a user interface change set tool. And basically, they would just need to open it and select the LAN and the switch or switches that they want to apply the change to, and then basically generate a diff between the select devices, running the configuration and the respective new candidate configuration generated by the platform based on the data that is retrieved from the inventory. And then after they review the diff, basically they decide if the change is what they meant or not. And finally they just apply the changes, basically rolling out the new candidate configuration. Yeah, so if we open, so basically this is the kind of black box. If we open the black box, we can see it's basically composed by several different systems which are interconnected to each other. So on the left side, you have the data coming from both service inventory and hardware inventory, which is it's basically used by the platform through the API. And on the right side, you have the actual network, which is connected to the platform through the Napalm library. Has been mentioned already before in previous presentation. So basically Napalm is a Python library that provides an abstraction layer between the switches and the platform. And it supports multiple vendors. And it is also nicely integrated with configuration management tools like Ansible, for instance, or Salt, as been mentioned before. Yeah, so it's open source. So this is a great advantage because it allows basically us to extend it to different vendor when we're required to. Basically, we are actually doing it right now. As you can see here, maybe it's a bit little, but it's called Napalm OCNOS, and that's basically going to be the library for interacting with the edge core devices which run IP Infusion operating system OCNOS. We're currently developing that, and we are hoping to contribute on the open source library once it's ready, so that other companies can benefit from it. And the center, you can, actually, at the bottom you have the user interface, which is called Toolbox, where the network engineer access the change set tool, where they basically trigger the diff creation, review it, and then if they judge that is the correct change, they deploy it. And at the center, you have kind of the core, which it's Ansible. We have two main playbooks, one for creation of the diff and one for the deployment of the configuration. And at the top, you have the kind of most important Git repositories. So you have one for playbooks, one for the templates, and one for the configuration. Actually, the one for the configuration is mainly used for once we have a successfully deployed configuration, it gets committed and stored as a version history in Git, basically. And of course, each different component logs into Splunk, a centralized log system, so that everything can be checked. Yes, so of course, this form of automation presents some significant challenges, and I would say, first of all, is the fact that it's cross-team project, so involves software, network, and internal system teams, and it requires a significant level of cooperation and knowledge sharing across teams. Few examples, for instance, the network configuration knowledge, which is predominantly held by the network team, of course, it has to be shared among the software team for the implementation of the network templates. Another example is on the other side, the development practices had to be shared with the network team for the modification and maintenance of the templates. And of course, as well, the knowledge, the platform key components and how to effectively monitor them has to be discussed and shared with the internal system team. So of course, we had also plenty of hands-on workshop during both the design and the beta period in order to progressively introduce the new processes in the company technology department. And I would say probably the most important challenge was the preparation and validation of the data. So considering the fact that in a data-driven network, the network is run pretty much by the data, having reliable data is crucial because correct data brings correct configuration and vice versa. So of course we spent a lot of time checking the correctness of the data, and after many iterations refining templates, network templates and processes to cover all possible corner cases, we achieved a perfect match between running and platform generated configuration. And only at that time, we started using the platform to actively change the network. So we implemented a lot of safeguards in order to prevent cataclysm to take place. And future development, basically, it's, as I mentioned before, being able to support different LANs and, of course, different hardware from different vendors so that we take the full potential, basically, of the implementation that we put in place. If we quickly go through the safeguards, worth to mention, I think, the lock-in system. So we wanted to avoid two or more network engineers to perform, say, different changes to the same device at the same time. So we implemented through API and Playbook a lock-in system that prevents them to do that, and basically after a certain amount of time the lock expires and or gets released after a successful deployment, and someone else is able to perform changes. Also, everything is, as I mentioned, is logging through our central log system. Worth to mention that we have another kind of validation, very important. So we cache the configuration that gets generated through the diff creation, and we hash it. Then when we run the deploy playbook, we basically hash it again and check that that actually matches with what we stored in the lock APIs. And if it doesn't, of course, we don't push it. That prevents any possibility of introducing in the network any change that wasn't reviewed previously. And of course, we restricted the permission for what concern the access to the inventory and to the change set tool to only the people that are supposed to touch the network. Well, I guess we can, well, basically everything has, every component has a dev and UAT environment where we can actually test any possible change to both hardware and code, and the same goes for the templates changes. Last thing that I want to mention is the metrics from London 1. So in blue you have, in red you have the number of deploys per day, and in blue you have the number of routers that have been involved in those deploys. And this is since basically the launch. The running total is more or less about 1,100 and counting. And yeah, as you can see, quite significant number of deploys, and usually if you can notice some peaks, those usually were related to the days where there were some maintenance in the actual hardware of the network, since a lot of progressive change to configuration has been carried out in a short amount of time. And that's me. That's done. So any questions?
Any questions for Riccardo? No.
Okay, thank you very much.
Thank you.